So good morning, everybody. Welcome back to our exploration of divide and conquer method. Just to reiterate, in the divide and conquer method, we take our recursive solution and try to decompose it in the optimal way. And while decomposing it in the optimal way, our objective is to ensure that the computational complexity is minimized. And in order to do that, we may have to create some data structures, we may have to remember some past solutions, and there we actually may have to use various other kinds of techniques of data structuring, memoizing, greedy, etc., etc. And we just saw some simple examples of sorting. We will continue with two of the classical sorting algorithms. So the first classical sorting algorithm that you are all aware of, which we shall do now, is the merge sort algorithm. So the algorithm that we shall discuss now is the famous merge sort. We have already done the basic blocks of merge sort in our previous classes. Again, our recursive definition structure. This is the base condition. Here we have the base condition. Then we have the decomposition. Split L into two non-empty sets L1 and L2. And therefore we appropriately choose where to split. Recursively call on M1, recursively call on M2. So M1 and M2 are what kinds of lists? Can anybody suggest? M1 and M2 are already now sorted. Now we have already done an algorithm by which, given two sorted lists, we can do their union or combine or merge. And how much time did it take if L1 had n m elements and L2 had n elements? What was our this recomposition, which we called combine or merge? What was the complexity? What was the algorithm? Do you remember?
O of n.
Yeah, no. One is m, one is n. What is the complexity? List L1 is of size m and list L2 is of O of the
Order
any
of
one of them.
m plus n, sir. It would be
of n plus m.
M plus n, right? Whosoever said n, is it now clear that if this is m and this is n, it is O of m plus n?
Yes, sir.
And we already did that in our tutorials. And one way, we did it in two ways, if you remember. One way we said was when we remove one, compare the first two elements. Based on the first two elements, you decide whether one of them or both of them will go into the resultant list, and then recursively call it. That also can be written down in a recursive fashion, which we have discussed earlier. So that is not an issue. So based on this, our whole definition, our recursive definition of merge sort, which we now define as merge sort, which you all know, is if L is less than equal to 1, otherwise split L into L1, L2, merge sort L1, merge sort L2, merge L1, L2, and where to optimally split it, because the general condition will be n by k plus n minus n by k plus order n. And if we choose any n, any k which is a constant, that is if we break it up into 2/3, 1/3, 3/4, 1/4, whichever way you do, you can show that the overall complexity, because this is linear, the merge is linear, therefore the overall complexity will be order n log n. But if you do a more detailed analysis, then you can show that the optimal value occurs at the middle. So, are you all convinced that if I break it up as 1/3, 2/3, or 3/4, 1/4, even then merge sort will end up in order n log n complexity?
Yes, sir.
Are you all okay with that?
Yes, sir.
Anybody has a doubt? Good. So now we see that another way, once we open up the recursion, we see how the algorithm is decomposed in a top-down fashion and recomposed in a bottom-up fashion. How? As the recursion proceeds from this point to this point to this point to this point, you end up in singleton nodes, and these singleton nodes are merged into twos or threes, and then they are merged backwards. So once we see how the algorithm works, and we know that we can implement merge, the merge algorithm which we have, this can be implemented easily in two arrays. If we have two arrays and I have to merge array A and B, then I can just have two pointers, two indices, and store the result in C. Isn't it? I compare AI with BJ. The indices are at I and J. Initially, the indices are 1 and 1. And then I compare AI with BJ. If both are equal, I put both of them in C. And if I'm doing in ascending order, otherwise, if they are unequal, I take the smaller one and put it in C. And I increment the index of C. And I increment the appropriate index of the element which I have put in. Yes, Ishan, what are you saying? I think people are writing in the chat box. I cannot speak and see the chat box and do everything at the same time. No?
So,
Sir, actually,
So
for
you're not
some of
quite
us,
audible. Your voice is
No.
cracking a
like,
bit.
Is
yes,
my
sir.
voice cracking for everybody?
No, sir, that's what I was saying, that it's not cracking for me. So maybe it's a campus LAN issue.
Maybe. Because
I can hear very cleanly.
Okay. I'll try to speak a little slowly. So implementing merge in an array is a straightforward thing. So now when we see this bottom-up approach, then we can see that if we have all our elements like this, then we take them pairwise and do a merging level by level from bottom to top. So at the first level of merging, I merge 7 and 3, then I merge 8 and 1, and this fellow is left. So in the next level, I will merge 1 and 5. Then I will merge 7, 3 with 1, 8 and 5 and get this result. Now this I can easily implement in two loops. One is the inner loop, which does the row wise, and the outer loop, which does the column wise. Is it clear to everybody that I will make an inner loop which does row wise and an outer loop which does column wise? Anybody has a doubt here, or is it okay with everybody? Can somebody tell me if it is okay or not? Is it
Yes, sir,
clear
it is
or not?
okay.
By the rows, you mean the levels which you have marked by
Yes,
3,
yes,
2,
yes.
1 and 0.
By the rows, I mean the levels. This is at every level. At every level, I have to do this composition, and this is level by level. Got it?
Yes, sir.
Yes. Now tell me, how many levels do I have? If there are
Log n.
n elements, how many levels?
So log n levels.
Yes,
Log n,
log
sir.
Log n.
Right. Log n levels. But now at every level, the number of merge calls will be different. At the last level 0, the number of merge calls will be n by 2. One level above it, the number of merge calls will be, at level 1, it will be n by
N by 4, sir.
4.
2.
No. At level 0, since I'm merging them pairwise, so there will be n by 2 merges at level 0, right? To reach level 1.
Yes, sir.
No, somebody who said to at level 1 n by 2. So I will have n by 2 such merged pairs at level 1. And then how many merges will have to be called at level 1? So here I will call, here I will do n by 2 merges. Here I will do n by 4 merges. Here I will do n by 8 merges, and so on and so forth till I do 1 merge at the final end. Okay. So 1 merge will be required at the final end. Now, is that clear to everybody? Anybody has a doubt at this point in time?
No, sir.
Excuse me, sir.
Yes.
I have a doubt,
Huh.
sir. I have a doubt at when we are at 7 and 3,
Hmm.
then why we are splitting them? Why
We
just
have
not
no,
compare them?
yeah. So that is our, you can do that. You can compare even 10 elements at a time also.
Okay.
Alright. This is just a base condition we have taken because we know that if we have 7 and 3, then also we can do it in order n comparisons. It does not change our complexity.
Okay. Okay. Okay.
Any other question?
No, sir.
Okay. So if there is no other question, then at every level, suppose at level 0, I have n by 2 merges of how many elements?
N elements.
Of 2 elements each. Isn't
Yes,
it?
sir. 2 elements each.
So my merge cost is n. At level 1, I have n by 4 merges of
4 elements.
4 elements each. So what is the merge cost?
N.
N. And you can show that at every level, my merge cost is n. And there are how many levels we have already seen?
Log n.
Log n.
So another way of finding out what is the complexity is merges at every level multiplied by number of levels, which becomes again n log n. So what we can do is we can have all the elements in when I go to my data structures, we can have all the elements in an array and the indices of the call will indicate which portion of the array the call is for. So now when I split into two equal parts, wherever I split into two equal parts, if I have the array index ij, then I will split it in the middle. I will do I plus j by 2 and I will choose one from I to I plus j by 2. The other I will choose from I plus j by 2 plus 1 to j. And that is how I will get my loop structure. So by using only one array as my argument, I am trying to develop this algorithm. Can you tell me, have you understood this part? That I will use one array and then I will split here and I will just call it on that same global array. So I will use only one global array as data structure and I will then start passing the arguments only the I, j, and this is I plus j by 2. I will just pass the array indices and my algorithm can work only using array indices. Is that also clear? Abhishek Gujjar? Abhishek Gujjar? Arunava Sarkar? Is it clear? Arunava, I can't hear you. You're trying to put your mic on, but I can't hear you. Write in the chat box. Vaibhav Vikas,
Yes, sir.
is it clear? Do you have a
Uh,
doubt?
no, sir, but I have just joined, sir.
Oh, you have just joined. So what were you doing so long? We are 20 minutes into the class. Was some class for 20 minutes earlier?
No, sir, actually network issues.
Bhagyashree Sharma,
Sir.
Yes, sir.
are you okay up to how much we have done?
Yes, sir.
Sure, you have understood this bottom-up two-loop algorithm with an array?
No, sir, but I will look it again and then.
Devraj Das Adhikari, Gaurav Jha,
Yes, sir.
is it clear?
Yes, sir.
Okay, tell me, Gaurav, I have one issue. We will now write an algorithm merge which will call an array A with how many arguments will be there now for merge?
So let me.
Huh?
Could I take 1 minute, sir?
1 hour?
No, sir. 1 minute, sir. Let me think, sir.
You are thinking of something else. You are not in the class. Taking so much effort to teach the class is futile if this is the way you all will react. And let me tell you that I will just complete the syllabus. All right. And then you all read up because the hard way is easy for you. The more I have seen, the more we try to explain to all of you, the more you relax, you think your baad mein pad lenge. So let me go very fast and finish everything today. Is that all right with everybody? Let me just go very fast, complete everything so that you all can read up the book. Slides are there, everything is there. All right. So that's fine. So I will leave it to you to figure out what you have to do. Read a standard book and you try to work out. I said that you can implement it in only one array. One array implementation. But try to see if you can really implement merge in one array. That means if I give you to merge an array A and B, if I give you a merge algorithm which will have an array A and indices I, J, K and L, where I have to merge Ij and Kl, and obviously in our current algorithmic method K is equal to Ij plus 1. So because K is J plus 1, merge will have these 4 index arguments, but try to do merge of an array I with indices from I to J and from J plus 1 to L. Try to do that merge in that array itself in order n time. So in place merge. I have now decided that there is no point trying to spend so much effort with all of you. Nobody is interested, and you all will anyway learn it the hard way. So try to do in place merge in order n time. And you will find that this is a very difficult problem to solve. Not that it is not possible, but it is very difficult to solve. That means whenever you try to use merge, you typically need to use an additional array where to store the merged elements. Only then you have a simple mechanism of doing it in order n time. And if you try to do it in that same array, then you will end up in a lot of difficulty. So please read up. There is a lot of research and literature in place merge in order n time. The next problem that we start talking about is called the optimal merge sequence. The optimal merge sequence is as follows. The definition is that there are lists L1, L2 to Ln, Lk, which is generalizing the merge problem. That means instead of 2 ordered sets or 2 ordered lists, I now have k ordered lists and I have to merge them. So how will I merge k ordered lists? So my objective is that I will merge them pairwise. Now let us see if I merge them pairwise, what happens. Take this example. Can everybody see this example?
Yes, sir.
Yes, sir.
I have to merge L1. This is the list L. L1 is the size, Li is the size of L. Li is the size of L, of capital Li. Small li is the size of capital Li. So list 1 has 7 elements, list 2 has 6 elements, list 3 has 2 elements, list 4 has 12 elements. Now I have marked the possible mergings in different colors. If you see the red color, then I am merging 7 and 6 first. Then that gives a list of size 13. That I'm merging with a list of size 12, which gives me a list of size 25. And that I'm merging with a list 2, which gives me the final merged list of size 27. The other option is the black line, where I merge 2 and 12 to get a list of size 14. Parallelly, I merge 7 and 6 to get a list of size 13. And then I merge these two merge lists to get a list of size 27. The third option is that I merge 6 and 2 to get a list of size 8. I merge a list of size with the list with size 7 then I merge the list with size 27. The fourth option is I merge 7 and 12. Then I merge the result with 6 to get 25 elements. Then I merge with size 2. There may be other options. All these methods are going to yield the same final merged list. The result is the same, but the number of computations to obtain the final merge, that means the number of comparisons to obtain the final merge, is different. How are they different? Take the red color. In the red color, when I merge 6 and 7, I get a list of size 13, so its cost is 13. M plus n. Then I merge that with a list of size 12 to get a list of size 25. And that is 13 plus 12 is 25. Then I merge this list of 25 with this list of size 2 to get a list of size 27, and my merge cost is 27. And my total merge cost is 65. Similarly, for the black line, my merge cost will be the first merge 13, the second merge which is done in parallel 14, and the third merge 27, which is 54. Similarly, you have this method which will yield, the blue method will yield 8 plus 15 plus 27. All of them will have 27 at the end because that is the final result. And the purple method will have 61. So now it is clear that the order in which I do the merging will affect my final complexity. And therefore, I need to find what is called an optimal merge sequence. Can anybody recall which other problem we had where we wanted to find an optimal sequence? Does anybody remember any problem?
Sir, matrix chain multiplication.
Matrix chain multiplication. Good. We'll come to that problem. We have not come to that problem.
Sir, maybe we can also say the bottom-up thing which we just did 2 slides ago.
Yes. Yeah. What are we saying about bottom-up thing?
I'm saying here also I think we are taking the optimal things, sir.
Yeah, here we know that we are doing it in n log n. We'll come back to this. Here we are only merging. We are merging a sequence, and if we did not, we now have to prove that we are all. This one is also an optimal sequence, which we will come to by arguing about the. First, we have to find in this problem for a general list of merged list, what is the optimal way of doing it? Can anybody suggest what is the optimal way? How do I do this? How do I see here? I can find the solution to this problem by looking at all options and finding out the option. Is there something here where I can solve this problem by divide and conquer? How divide and conquer? I can break it up into different ways in which I can merge. I can first say I'll merge 7 and 6, then I'll merge 6 and 2, I'll merge 2 and 12. I will compute how many are required. I'll just compute how many comparisons are required. I'll not do the merge algorithm. And from this list, I will find out which is the optimal. From this 65, 54, 50, 61, I will compute all of them and find out which one is optimal. Do I need to do that? Do I need to look
So we
at
can
all?
take the minimum.
No, sir. You can take the
Maybe
smallest lists and first merge them.
So for the first statement that some of you are making is that you take what is called what kind of an approach?
Greedy approach, sir.
Greedy choice.
We take a greedy choice. We take a greedy choice of options. What is it? we first merge, we look at the smallest size lists. We look at the smallest size lists and merge them. So in this case, which are the two smallest size lists?
8 and 2.
6 and 2.
6 and 2. So we merge 6 and 2. We'll get a list of size 8. So now there are three lists, one of size 7, one of size 8, one of size 12. So if we merge 6 and 2, we now end up with this list of size 7, a list of size 8, and a list of size 12. Now which two we will merge?
7 and 8.
7 and 8. And then we are left with two lists, one of size 12, one of size 15, and we have no other option but to merge them. And if we have done it in that sequence, you can see that we have obtained 50, which means that at least in this example, it is the best. The question that you have to prove is that this greedy choice guarantees to give you the best. Can anybody tell me the proof?
So,
Yes.
I have a question. So instead of taking a greedy choice, can we not say that we must first start with merging the size lists, but then we should merge it with the
first
next
start with
smallest
merging
list in the
the.
sense.
No, I couldn't hear. We start with merging the.
So we first start with merging 6
and 2. Yes. Then.
Yes, sir. But then we merge with the next smallest original list. So so like 6 and 2, and then we choose a 7 instead of.
Then you choose a 7 with whom? Let's take another example.
So we merge the 7 with the.
With whom? Suppose Ishan, take another example. One list is of size 7. Huh? Let us take another example. This is a list of size 7. There is a list of size 2. There is a list of size 2. There is a list of size 4. There is a list of size 4. And there is a list of size 12. Now, Ishan, which two will you merge first? 2 and 2.
Yes, sir.
And then 4 and 4. Okay, let me take this.
4.
Let me take this as 3 and this as 4. And this as also 5. This has 5. So now which one after this, which one will I merge? 3 and 5.
So 4 and 3.
Yeah, so 4 and 3. So that is what we are doing. Now, once I create merge 2 and 2, 4 and 3 will be my minimum. Now which two will I merge?
So then 7 and 5.
That's what we are doing. You take any 7, it does not matter. Then?
Yes, sir. Then a 7 and 12.
That's the algorithm. That's what we have been talking about.
Yes. So, but if supposing 7, 6, 2, 12, and 3 and 4.
7, 6. So let me write here. 7. Let me keep some space. 7, 6. Then
6, 2,
2.
12.
Then 12.
3 and 4.
3 and 4. So which two we will merge first?
Again 2 and 3.
Now which two we will merge?
5 and 4.
That's the algorithm, no? Now which two we will merge?
So 6 and 9.
6 and 7. You do 6 and 9, you will get into trouble. Let's do 6 and 9. Let's do 6
I
and 9.
understood the greedy. Yes, sir. I'm saying.
If you do 6 and 9, you will get 15. And then you do what? Next, what will you do? 15 and?
So then we take 7 and 15.
7 and 15. What will you get? 22. And then you
22.
take 12 and 22. What will you get?
34.
What is the total number of comparisons for this method? 5 plus 9 plus 15 plus 22 plus 34,
So
right?
75.
75. Now let's take the other one which we did not follow,
Yes,
which was
sir.
our. So you will do 2 and 3. Then you will do, instead of doing
5 and 4.
5 and 4, then
7 and 6.
7 and 6, then 12 and
9 and
9,
12.
then 13 and 21, which is 34. Now count how much are there? How much?
34, 34, 68, 68 and 9, 77. So I'm getting 82.
So
In the
the
first
first
one,
In that case, we get 85.
75 is 85. Yes.
this is 85. Ishan, this is 84
Oh, okay, 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 sir.
and this is 85. Got it?
Yes, sir.
So this optimal merge sequence, the algorithm says, choose Li and Lj such that the size of Li and Lj are the smallest size in the list. And you can prove that this greedy choice is already optimal. What is the complexity of this algorithm? This also I will leave it to you to do. And if you look at merge sort, as somebody just said, merge sort, what does it do? The merge sort algorithm, which that bottom up algorithm. Now, whosoever was saying that, Shivam or somebody was saying na, that this merge sort does the same thing. Who was saying?
I said, sir. Sai
Yeah,
Sharad.
Sai, Sai Sarath. See, that is what is happening here. First, all lists of size 2 are merged. Then again you are taking the smallest lists and merging them. And the merged lists are growing because they are doubling up. Because the merged lists are growing and doubling up. So this algorithm, bottom-up algorithm, as you have rightly pointed out, is also doing the optimal merge sequence. Is that what you were saying?
Yes, sir.
So the bottom-up algorithm, that is why I brought this optimal merge sequence problem, because the bottom-up algorithm is doing the optimal merge sequence in any way. So we have ended up doing merge sort. At the end, we know that we can use a global array, but can you hear me now? Hello?
Yes, sir.
There was a blip in between.
Yes.
Yes, sir.
Yes, sir.
Yeah. So now, and from this we reached here, but the few open questions were there. First question was, can I do everything in place in one array of size n? And that is a non-trivial issue and beyond the scope for the moment. The other alternative for the optimal merge sequence, again what we discussed the other day, is that we choose from L1, L2, L3 up to Ln, we look at their first elements, we choose the minimum and put it in the final result. Then again we choose the next minimum and put it in the final result. Again we choose the next minimum and put it in the final result. What will be the time complexity? A brute force time complexity, if you find the minimum by normal method, it will be like this. Every time the minimum will take order n time and you will get an order n squared algorithm. But we have already done something by which we can create a data structure where we can insert an element and remove the minimum. What is that data structure we did yesterday?
Binary search.
Balanced binary search
search.
tree. So if we use a balanced binary search tree, all we will require is to create an initial binary search tree with the first elements. So we will do a set of insert operations. Then, so we will do a set of, if there are n such lists, we will do n inserts first. And then what is the next operation that we will do? Remove min. Find min and delete. And whichever list the minimum came from, what we will have to do? What will we have to do?
So maybe update the pointer.
No. We have got n lists, all sorted lists, right? We are to merge them into a final result. So what we have done is we have taken the first elements and put them into a binary search tree.
Yes.
And once we remove the minimum element of this binary search tree, we get the first element of my final list. Once I remove, I get the first element of my final list. And suppose that came from list L3. Then what do I have to do from L3?
So we will remove that element from the L3 and then insert the next element.
Insert the element based on which list it came from into the binary search tree. So we will go on repeating an insert and remove min sequence. And each such sequence, how many times we will remove? The total number of elements. If there are totally m elements, then my total number of inserts and remove mins will be of the order of how many such inserts and remove mins will be there? At most order m such inserts and remove mins will be there, because every element will be inserted once and removed once. Yes or no?
Yes.
And each such insert and remove min will take how much time?
Order of log n.
Log n. If there are n lists, order of log n. So my total complexity will end up as m log n. Now you have to compare how this method compares with the previous method that we talked about. Which method is better? Are both the methods same in terms of complexity? In which cases, if they are not same, then are there cases in which this one is better than that or that one is better than this? What are the cases where both are giving same complexity? These are the questions. So these are the two algorithms for optimal merge sequence. In the case of merge sort, both these algorithms eventually turn out to be the same thing. Because in merge sort, the size of the lists are all initially of size 2. Because the size of the lists are all of initially size 2 and then size 4, then size 8, you can show that whatever you do there and whatever you do here are identical. But it is good. That is, this is another alternative which is giving another complexity result. So how do I compare them? That again I leave as an exercise. Any questions?
So can you kindly repeat what was this M? N I got, sir. M.
M is the sum of, if Li is equal to size of Li, then M is equal to sigma Li. M is the total number of elements in all the lists.
Okay. And N is the number of lists.
N is the number of lists.
Yes,
So my
yes, got
binary
it.
search tree size will always be N, but every element will be inserted once in that binary search tree and removed once. So M operations, M inserts and M remove means will happen totally. So the total complexity is M log N.
Yes, got it.
Got it, everybody?
Yes, sir.
Yes.
Good. Now we come, so we discussed the greedy algorithm. How do we solve the greedy algorithm? What are the data structures, etc. We also did the balanced binary search tree algorithm. So all of you write down the final algorithms Look at the book for one for merge sort. That is, I want to see what is the iterative algorithm with that 2 loops. Second is the optimal merge sequence. And we have got 2 approaches, greedy and BST based. So please write down the final versions of all the algorithms by yourself and figure out the answers to the questions that we have raised. Now we move on to another classical algorithm. The difference between merge sort and quick sort. So merge sort takes an array, splits into 2 parts without doing anything, calls it recursively, gets back sorted lists, and then merges the sorted lists. Can anybody tell me what does quicksort do?
So it
Take up
finds a pivot element and then
Generalized quicksort, yeah. So it chooses some element. So it has the list L. It chooses some element xi in L, and then
sir it sorts it on the left side and right side
no.
recursively.
It does not sort it on the left hand and right side. It does something else.
So it keeps all the
Correct.
it's partitions the entire array on this basis on this pivot based on this pivot element. Like all the numbers lesser than this pivot will be on the left side, and all the numbers greater than this pivot will be on the right side. Then this is recursed on both the sides.
Y element of L such that y is less than xi. L2 is y element of L such that y is equal to xi, and L3 is y element of L such that y is greater than xi. And then you can replace L1 and L2 by using the less than equal to sign. So we don't bother about this now for the time being. But you could do 3, you could do 2. So let us do L1 and L2 like this. One is less than equal to xi, one is greater than xi. So now In merge sort, when we split it, we didn't do any pre-processing. Here we do a pre-processing. And this is the pre-processing that we do, that based on a chosen element xi, we split the list in such a way, or this is called the partitioning of the list. We partition it such that it is one is all elements less than equal to xi and one is all elements greater than xi. Is this what you were saying? Somebody who said this?
Yes, sir. Yes, sir. Yes, sir.
And then what do? Now you recursively call it on L1 and L2. So your decomposition function is partitioning, your recursive calls, and then when you get back the result, what do? You get back the two sorted lists, what do we do?
We merge it
Combine
with
them.
X1 and
What is this the same merging algorithm required that you used in merge sort?
No, so simply L1 xi and L2.
L1 followed by L2. If once you call it recursively, you get back M1, and for this you get back M2. All you have to do is just write M1 followed by M2. It will give you M.
So with
Because
the xi,
no, I have taken less than equal to, so that is not a problem. So all the xi is in L1. The xi is in L1.
okay, sir.
So I recursively call it and I get back the two lists, and all I need to do is concatenate the two lists. So my decomposition function is partitioning and my recomposition function is just concatenation. If I choose the pivot element xi, what is the complexity of partitioning and what is the complexity of concatenation? Partitioning will take how much time? If there are total n elements in the original list, partitioning will take how much time?
And
Order n.
So n, order n,
And concatenation will take how much time?
constant time.
Order 1.
order 1.
Right. So now I have a very similar equation that I had in merge sort. In merge sort also I had T n equal to 2 Tn by 2 plus order n. Here also I have now got the order n because the decomposition plus recomposition is order n. But where is the catch? Where is the catch?
2T n by 2.
Yeah, the catch is 2Tn by 2. The catch is 2Tn by 2, which means that I have to choose a pivot element which splits the list into
Two completely equal halves.
two completely equal parts. What is that element by definition? An element which splits the list into two parts.
Mean of the
The
list.
mean.
Mean.
Median.
The median.
So the median.
Median. I need to find the median. So what is the algorithm to find the median? You will say sort the list. If I sort the list, then so there is no problem left to solve.
We can do that finding maximum, like finding first max, second max, third max. We have to find n by 2th max.
So if I find n by 2th max, let us do that. Let us do that. Good idea. Suppose I find n by 2th max. So median finding, that is where is the catch now. For quick sort, median has to be found. Now if I use binary search trees, then I will get an algorithm which is n by 2 log of n.
Uh,
This is
yes.
order
And log n.
n log n, hai na?
Hmm.
So my algorithm complexity will become Tn is equal to 2Tn by 2 plus order n log n हो जाएगा ना?
Oh.
Because this is order n log n plus order 1, which is the same as 2Tn by 2 plus order n log n. By master theorem and by analysis, this becomes what? Order
N square log
n log n squared, right?
n square is.
So this algorithm for median, will it do?
No, sir.
It won't work. It is worse than merge sort. In order to achieve,
So first we can do is that we can take any element to be the we can initially we can use any element.
if you use any element, that element may split up the list into 1 n minus 1.
Okay.
If you split up the list, you take any element, in the worst case, it will become split as,
Okay.
and this will yield you order n squared complexity.
Hmm. Hmm.
So what is the challenge? The challenge is to find median in order how much?
Log n.
नहीं log n में तो आपका निकलेगा ही नहीं. If you find it in order n time, you're done. Na? Then you will get Tn equal to 2Tn by 2 plus order n, which will give you order n log n. If you find it in order log n time, then your algorithm complexity will become order n by master theorem. Then you will get a linear time sorting algorithm.
Yes, sir.
So this is the challenge. For the time being, you just know from me that such an algorithm exists. It is one of the most interesting algorithms in computer science. It is itself a divide and conquer algorithm. But a non-trivial divide and conquer algorithm. The way you divide the problem is very unique. Here you divide this into 5 or 7 sets, and then you recursively find the median of these sets. And then you use the median of all the medians and merge them together to again find something. And finally, you end up using that master theorem to show that you can solve this problem in order n time. So this was a very famous algorithm by Robert E. Turgeon and others. He is one of the persons who's also got the Turing Award in computer science. For many other things, one of them is this. One of them is the best algorithms for set, union, and find. So the ones union intersection that we all did, there is another problem called the disjoint set union, disjoint set union and find. which we tried to do briefly and we came up with the binary search trees, there is another interesting data structure which says if all the elements are disjoint, then this union and find can be done even faster. So these are all very powerful, almost linear time algorithms. And these are very complex algorithms which are not part of the first part. But while we reach the end of the course, we will teach you both. We will show you both this divide and conquer algorithm as well as the disjoint union find algorithm, which are the most advanced data structures and divide and conquer algorithms. So for the time being, you get to know from me that such an algorithm exists. But this algorithm is fairly difficult to write. So just to recap, so this algorithm is fairly difficult to write. We want to find median in order n time. Therefore, if we can do that, and we know that we can do that, we will be able to get this quick sort also in order n log n time. On the other hand, if we choose a random element instead of choosing the first element, if we choose a random element as the pivot element, then we can show that a choice of a random element as pivot will yield an average case complexity of n log n. So we can show another thing, that is choice of a random element as pivot. When I choose a random element as pivot, then nobody can create a worst case example for me. So if I choose a random element for pivot, then on an average, quicksort takes order n log n time. How do I show this? I show this by assuming that the problems are from a uniform distribution, and my list can break up as 1n minus 1, 2n minus 2, 3n minus 3, 4n minus 4, and so on and so forth. And if I do that, and I will sum up all of this and take the average. If I sum up all of this and take the average, because the worst case occurs only in 1 by n of the cases or 2 by n of the cases, therefore, on the average, the worst case does not happen. And because I'm choosing a random element, you can only produce the average analysis. And that average analysis is done in Corman and other textbooks. I will not do that average analysis for you. But we come to the conclusion that quicksort definition is like this. There is this base condition. Then we choose an element y from L. We break it up into two sublists, L1 and L2. We recursively call it on quicksort and we concatenate. And we know that in the worst case, if k is 1, the algorithm will yield order n squared. The other is, if we can find the median in order n time, then the algorithm will become n log n. And the other case is randomly choose the pivot y, then the average case will again be n log n. So what has been found is that quicksort, if you randomly choose the pivot, then it is an in-place algorithm. That means you don't need any additional array to partition the array. Whereas in merge sort, you typically require, if it's a straightforward algorithm, you typically require an additional array unless you have a very complex algorithm. So the median finding in order n time is a linear time algorithm, but for practical cases, it runs more time than an average case algorithm does. So the typical examples of quicksort, which are done by randomization, actually on the average case using a single array run very, very fast. That is why quicksort, though it has an order n squared complexity in the worst case, it is a practically very widely used algorithm. Any questions?
Excuse me, sir.
Yes.
Sir, can you please explain the in-place merge sort algorithm?
In place merge.
Yes, sir.
Let me tell you, I have got an array A. This is array A index 1. This is array A index n. And this is n by 2. Assume n is even for the time being. All right.
Yes, sir.
Now, this is sorted. This is sorted. I want to make, so this is array A. I want to merge A1 n by 2 and A n by 2 plus 1 n to sort A without any additional array. Is the problem statement clear now?
Yes, sir.
Tell me how you will do it. Previously, we were comparing the two and putting the result in a second array, isn't it?
Sir,
Now,
like,
where will you put it?
maybe obviously we'll have the pointers for the first and n by 2 plus 1 element. Now we compare both those elements.
Correct.
And if, for example, the first element is small, then, I mean, assuming that we need to sort in ascending order, then it's going to be there. But maybe if the n by 2 element is, I mean, n by 2 plus 1 element is smaller than the first one, then we put it in the first place and then maybe shift the whole of first half. Something like that.
Once you start shifting the whole of first half,
Yes, sir.
then for one step of merging, you required order n operations.
Okay. Yes, sir.
We can,
So
like,
if you have
we
to
can
do
take a,
n steps of merging, then you'll end up with doing merging in order n squared time.
Okay. Yes, sir.
we can take
Got
a
it?
temporary element and then do that.
Huh?
We can take a temporary element and then
Take
do that.
now. Take a temporary element and remember what?
I mean, after every two comparison, remember who was the greater element, and then
Who are the
like for
greater element you know anyway. You tell me an example of what you will do, I'll give you a counter.
okay, so for example, first I will so there are two parts, and then I will take the first two elements and then I will compare them. And if the first one is smaller, then
You do nothing.
I do nothing. But if the first one is bigger, then I replace the first element with a smaller one and the value of the first element in the memory, I mean in the temporary variable.
Okay,
And
I'll
then,
remember temporary variable, I'll remember the first element. So let us say this was 2 and this was 4. Sorry, this was 4 and this was 24. So I remember 24 and I've put 4
yes.
here. I've put 4 here
Yes,
and I remember 24. Now?
And
Now, whom do
now
I compare? I have now got to compare which one? 24 I will compare with whom?
I will so we have 24 and now
Now, so next element is 5. Bolo, ab kya karega?
yes, next element is 5 and the next element for the second one is
So
also
where will I
something.
put 5? What will I do with 5? Will I put 5 in the beginning of A after 4?
No, we also need to know what is the next element after 24.
Okay.
No,
We now
okay,
need
it
to
will
know
be
what is the next element after 24. So it is 27. Bolo. Now what to do? Now you will compare 24, 27, 5.
Okay. So it's keeping a comparison. Okay.
Got it? Complicated, है ना?
So maybe we can compare 5 with the temporary 24,
And then?
since their 5 is smaller, we now put, okay, if we put 5 and 27, we lose 27. So
समझ गया? It's not trivial.
Sir, or else like I'm talking about not without using this temporary variable case. Like we can just, like, for example, if we have 5 and 24, and like because 24 is greater than 5, and then we put we like change the pointers, like we give 5 the first pointer and 24 the other pointer, and then increment all the pointers in between.
From where? Pointers are 2 pointers. 1 pointer for the first half, 1 pointer for the second half.
Yes, sir. I mean, I'm telling to increment all
So
the pointers from
am I using a temporary variable or not? Tell me. No, let us go straight. We are discussing what somebody else started with. Are we using this method of this temporary variable or not?
Yes, sir. So maybe we can place the 24 where 4 was.
Where 4
now
was?
That we've seen, so
now
that
we will
we've seen
replace
that
4 by
is,
24.
Yes, sir. And we place the 27 in the T because now we've kept the 24 there. And now we move to 5.
I will make you another example. You will get confused because you are losing track of where you are. So you have kept 24 here, 5 is after 24, 27 is here, and now you'll put 5 here.
Yes, sir.
The next element is 6. The next element is 31.
So now I know for sure that, yes, sir. Now I know for sure that the 24 is something which I need to deal with later. So I now compare 6 with 24.
Correct. 6 with 24. Why? How do you know you have to compare with 24? You have kept 27 here. You have kept 24 here.
So because I'm keeping the smallest element.
Okay, so now you'll compare 6 with 24, and we'll store what? Which where? Well, this is 31 is here. Where will you store now 6?
So I'll put the 27 where 5 is.
You'll put 27 where 5 is. Then
I will put 31
here.
where T is. 31 where T is. Yes, sir. 6 at 31 and
here
31 where T is.
Where T is, and 6 here.
Yes, sir.
The next element is 96.
So I again compare 96 with 24.
कहाँ है 24? How
so
do I know that this 20?
Okay. So
now I compare 96 with. So no. Let me make it instead of 96. Let me make it 28. Now what to do?
So compare with 24.
And then put 24 here, 24 there. You are going to get confused. Are you samjha? The more you do, the more example I will create.
Yes, sir.
So I'm just trying to convince you that this is not a straightforward thing to do. So read about in-place merge, and if you can solve the in-place merge in order and time in a clean fashion, then I'm sure, let me know. I'll be very happy to discuss that algorithm. So will Palash. Okay? It's an open question. How well can you make in-place merge? It's still an open question. Good, y'all are getting good ideas. But it's, Ishan, have you understood that it's not so complicated? I will now start switching the elements. You won't know how to keep those lists. Chalo, very good. So as a summary, another important thing is that many other of these algorithms that we wrote, if it, see, when we did max removal or insertion sort, for both of them we require data structures. Other than the original array, we require data structures. For merge sort also we saw that other than the original array, we require some additional place to do merge. And for quicksort, we found that this median finding itself is a problem, and can we do it? So this additional space to do sorting in order n log n time, can sorting be done in order n log n time without additional space? That is the open question. That is the open question. The second open question when we do lower bounds is the other question. Can sorting by comparison be done faster than order n log n? We know, like we did the maximum element, finding the maximum element. We proved that you cannot do it faster than order n time if it is an arbitrary unordered list. Similarly, the question comes for sorting. And these questions we will answer when we discuss lower bounds. But now we are trying to understand methods and raising the issues. So with this, we come to this end of this part. Any questions? You can stop the recording. We'll break for 5 minutes and restart. Anybody has any questions? Or think of the question.